Alright, today we'll be talking about current of electricity. This is technically the second chapter in electricity, but it is, I would say, the foundation chapter for your electricity. As I described to some of the other students, this chapter is you learning all the foundational knowledge that you need for the next few chapters of electricity. So without this chapter, it's as if you are trying to do kinematics chapter without understanding what is distance, or you have no concept of what is time. So calculation of speed is impossible. So this chapter is important and it lays the foundation for your future study of electricity. Alright, so these are the four main components of this chapter. There is some prerequisite knowledge that you need to know, so I'm just gonna refresh your memory on what they are. First few things that you need to know is charge. Electrical charge is given by Q. You learned this in the chapter before, static electricity. Unlike charges attract and like charges repel. In your study of kinetic model of matter, you also learn that all matter is made out of tiny particles. We know them as atoms, alright, and that they are in constant motion. And finally, some mathematical knowledge. When you have a graph, y, this will be your y-axis and this will be your x-axis, and if it's a linear graph or a straight line graph, then your equation of the graph is given by y equals to mx plus c, where m is your gradient and c is your y-intercept. Right, so with that, we have all the knowledge we need to start our study of current of electricity. Right, so let me just discuss our first part, which is electric current. So what exactly is electric current? Electric current is actually formed by just moving electrical charges. So electric current, you can think of it as a measure of a rate of flow of electrical charges, which means it's just a measure of how many charges pass by you in 1 second. Alright, you know that in your study of static electricity that one charge is measured in coulombs, and that one electron or one proton, basically one charge based on its particle is given, or rather it has a value of 1.6 times 10 power negative 19 coulombs. Alright, which means that you need an intense or quite a large number of these elementary particles, either electrons or protons, flowing for you to even just have 1 coulomb. Alright, so current is then given by the rate of flow of charge, which means how much charge pass by in 1 second. So you take the number of charge passing by in 1 second divided by time. The unit of charge is coulomb, the unit of time is seconds, which means actually the unit of current is coulomb per second. But it is a mouthful, so we just reduce it into something called the ampere, and it's abbreviated with a big A like this. Now, before the discovery of how an atomic model works, we did know, or human beings actually utilize the use of electricity already. So the only thing they didn't know was that they knew there were these particles that were moving around, and they knew that these particles carried the energy, and they called these particles charge. Now they just didn't know, based on their understanding at that point in time, whether it was the positive charges or the negative charges that move. Of course, now most of you study your basic chemistry, you know that your atom is made out of a nucleus which has the proton and neutron in the center, and you have electrons orbiting around. So the electrons are the one that we discovered are the one that flow. Now, based on their knowledge at that time, by convention, they said that, or they assumed that it was the positive charge that was moving. Now, we now know that's a wrong assumption, because we know actually it's the electrons that flow and the protons are actually in the nucleus and they make the core of the atom and they don't move. Alright, which means then, based on the knowledge that they had at that time, they had already formed all the batteries and they already set their convention as positive and negative, because when we follow this definition as defined by what they decided or what they guessed to be the correct answer, the flow of positive charge means that our definition of current is that it will flow from positive to negative. Now, why does positive charge flow from positive to negative terminal of the battery? Because of your prerequisite knowledge, what you learn, unlike charges attract and like charges repel, which means if I have a positive charge here, then it will repel from the positive part of the battery and it will be attracted to the negative part of the battery, because unlike charges attract. So based on this convention, they had basically the whole world went along with it and decided, yes, we think it's correct. We made a guess lah. It was only it's a 50% chance basically, either positive charge or negative charge. But turns out later they were wrong. So therefore, they then just decide, since the whole world has already gotten used to this, we will just continue to use the fact that we assume current was moving from positive to negative and the flow of positive charge. We just rename that as conventional current, because it was decided as a convention that it was the positive charge that flow. But in reality, you know, or you must know, that it is the electrons that are actually flowing. Now, henceforth, for all future mention of current in all other electricity chapters and this current chapter, you must know that what we are referring to is conventional current, which means the current that is flowing from positive terminal of the battery to the negative terminal of the battery. Now, how does one measure electric current? We measure electric current by the use of something called an ammeter. Now, this is the old school ammeter that you may see in the lab. This one is called a multimeter. Alright, a bit more advanced. I can do a lot of measurement of all different electrical physical quantities. Now, some important things to take note about ammeter. The ammeter should be connected in series to the circuit. What does it mean for it to be connected in series? In series means there's basically only one possible path for the current to flow. So if you look at this, now I'm saying current, so we're talking about conventional current, which flows from the positive terminal of the battery to the negative terminal of the battery. There is only one possible path for the current to flow. We say then they are in series. Because the ammeter is in series, that's why we place it like this. Now, why does the ammeter, which is a measurement of current, have to be in series? First thing first, you must remember, or we must recall, that current is actually just the flow of electric charges. Basically, this ammeter needs to be in the direct path of the charges as they are moving along the circuit for them to count how many charges are passing by in a second. And then they are able to give that value of ampere, alright, which is just coulomb, how many coulombs is passing by you per second. That's why we actually need the ammeter directly in the path of the current. That's why we put it in series, because that will place it directly in the path of how the current travels. Now, the ideal ammeter is one that has zero resistance, because we do not want the ammeter to actually cause, and I'm going to introduce resistance later, we do not want the ammeter actually to cause any blockages or slow down or take up any of the energy that the current has. Right, so we'll talk about a little bit about energy later on. It may not make that much sense to you right now, but it will later. Now, the main components of a circuit, typically you have something that gives energy to the circuit, which then moves the charges around, and that's usually a dry cell or a battery, a conductor that connects, wires, a load, later I'll talk about this, a method of opening and closing is the switch, and a load in which moving charges can do a useful job. You can just think of a load as an electrical component. Moving charges is basically, of course, your current. And useful job meaning is doing something and converting the energy the current has to do something else. For example, it is not limited to just bulb. A fan would also be the same, fall under this definition. Because a fan will take the energy the current has to actually spin itself so that it can give you wind. Right, cool you down. So basically anything that changes the energy the current has into doing some other form of energy for it to do something useful, then we call that a load. Now, electrical circuits can be represented by circuit diagrams, and we need circuit symbols to be able to draw circuit diagrams. Now, just for you to take note, the longer side of the battery in a cell, or rather the longer side in a cell, is always the positive side. The shorter side is always the negative side. That's how I used to remember things. And if I want to connect the ammeter, the negative portion of the terminal must be the one directly in contact with the negative terminal. And the positive terminal must be then directly in contact with the positive terminal of the battery. Now, you may then question what happens if you connect the ammeter wrongly. That means you connect it positive here and negative here. What actually happens is that if you connect it wrongly, That means this portion is connected to the positive side of the battery, and this portion is then connected to the negative side of the battery. What happens is that the needle here will actually just basically go down below zero, right? Because that means the current is flowing in the direction that will actually push the needle in this way. You can think of it that way if it simplifies the way that you want to remember. So if you do then later change the connection so that this is the negative terminal and this is the positive terminal, then the current is going to flow in a way that will push the needle in the correct direction that will give you a reading lah. So what happens if you have connect an ammeter during your practical and it goes basically below zero? All you need to do is just take this connection and connect here, and this connection and connect here. You just swap the connection of the wires from here to here to here to here. Alright, now these are some of the common electrical circuit diagram symbols that you need to know. The ones that are commonly used in the upcoming chapters, I already highlighted them for you, so you do need to memorize all of them. A galvanometer. What exactly is a galvanometer? A galvanometer is just an ammeter where the needle or the zero is actually in the center of the scale. It is able to give you values of current no matter whether you place it in the correct direction or the wrong direction. If you place it in the wrong direction, it will just give you a reading in this direction and your needle will actually go here. If you put it in you swap the connection, then actually the needle will go here. So it's just a tool for you to be able to sense basically the direction in which the current is flowing. Alright, so based on interpretation of circuit diagrams, a circuit is this is an open circuit is when I have a gap in the circuit, which means no current can flow through. A short circuit is when I have an alternative path that will allow the current, as it flows from the positive side to the negative side, to bypass the original component and take another path across it. Basically, in a sense, taking a shortcut lah. Alright, so a thing for you to take note that will be useful for your next chapter is that the lower the resistance of the path, the higher the percentage of the current that is going through it. Which means if I have a resistance wire or wire of zero resistance, that means 100% of the current will flow through it. Which, if you think about it, makes sense, because if I have a path here, one path here gives resistance, while I have another path here that gives basically no resistance, the charges are just going to take the easier path and make their way around. Alright, so which brings me now to the second portion of the chapter, which is electromotive force and potential difference. Alright, the next portion of this chapter is talking about electromotive force and potential difference. Now, you know that for a circuit to work, you need to have a battery and a load, basically, a component that takes away the energy, and you have connecting wires to also allow the current to flow. So the question now becomes is what exactly is the role of the battery in the circuit? Now, the battery in the circuit, some of us may wrongly think that it is the provider of the charges. Alright, so the question is, does the battery provide the charges that make up the current that then goes through the circuit? Now, the answer to that is actually yes and no. While the battery may have some charges, but quite a bit of the charges is actually made up of all the conductive components of the circuit. The copper wires or whatever connecting wires you have will also have is made out of atoms, and the atoms are also will have electrons, of course. So and this will make up then the current of the circuit together with whatever charges electrons are in the battery. Now, so the main important role of the battery in the circuit is actually the function is as an energy giver to the circuit. So it gives energy to the charges so that the charges, which is the electrons or the electrons, can then move around the circuit for it to be able to do work. Right? So what exactly a battery is like, you can think of it, I think the best analogy that we can have for electricity is that of a water pump. So you can think of the battery as a water generator or water pump that actually brings up the water to a higher gravitational potential energy. Alright, the water then actually is your charges or your current. So in the sense, the what the pump is doing is the same as what the battery is doing. It is giving it energy, in this case gravitational potential energy. So now the current or the water has energy, and as it moves down and flows across any load, be it like in this case a water wheel, but in the electrical circuit it could be a lamp, a light bulb, a fan, a motor, anything. As the water flows down, it will give the gravitational potential energy into the load, and then it will be able to do work. The same like how when the current flows through any load or electrical load, it will cause it to do some work and give energy to the load. And then after all of that, the current will end up back at the lowest level, where it will then go back to the pump, be given energy, and the whole cycle repeats again and again and again and again. Alright, so the function of the battery is to actually drive or give the electrons energy for it to move through the circuit. And now we introduce the very first first part of this. We have two that we have to cover today. In this portion of the chapter, electromotive force. Now, the electromotive force, otherwise also known as EMF, it is symbolized with epsilon, the Greek symbol epsilon. You can also sometimes write it as E. Some people just write it as E.M.F. Alright, it's actually the work done by the source to drive a unit charge. Means 1 coulomb of the charge around the entire circuit. Now, I just then need you to recall what exactly work done is. So work done, if you recall from the study of work, energy and power, work done is just energy transferred or energy supplied. So essentially work done is just energy measured in joules. Now, if I look at the formula, the electromotive force is the work done, or rather the energy given to each coulomb of charge. That's why it's just work in joules to each charge per coulomb of charge, which means then the unit of EMF, if you follow this notation, is just joule per coulomb. But of course that's a mouthful. We reduce that or replace that, simplify it with just the unit volt. Alright, so what EMF is how much energy the battery gives to 1 coulomb of charge that is given by what EMF means. So essentially what it means is, if I have a battery that is actually 3 volts, for every 1 coulomb of charge that passes by, each coulomb of charge will then be given actually 3 joules of energy. Alright, and then as it has these 3 joules of energy, it will then be able to move around. Now, as it's moving around the conductor, there's actually nothing that is taking away its energy, because we are assuming that the conductor, or rather the connecting wires, have no resistance, right, which we will cover in the later part of the chapter. So I will not be losing any energy along the way. So up until it reaches this point, just before it hits the load, it still has that 1 coulomb of charge, still has 3 joules of energy here. Now, once it passes by, just like how we talked about in the battery pump here, it will use up all its energy at the light bulb, and then it will end up with 0 joules, and then it goes back to the battery, that same coulomb of charge, and the battery will just give it another 3 joules for it to repeat the process over and over and over again. So that is what EMF is. Now, how one measures EMF is through the use of a voltmeter, where you just need to take note that the positive terminal here must be connected to the positive terminal of the battery or the electrical source, and the negative must be connected to the negative of the battery. Now, just some common arrangement of cells, just a quick recall. Volt is also known as how much energy, joules given to each coulomb of charge. Alright, so if I have a series arrangement of 2 cells, alright, before it enters the first cell, this coulomb of charge will have 0 volts, or rather it will have 0 joules of energy. When it passes by the first battery, then it will have 1.5 volts, or rather each coulomb of charge is given 1.5 joules. If it passes by the next battery, then it will give it another 1.5, and up your 1 coulomb of charge here will end up having 3 volts after it has passed by 2 cells. So the equivalent energy given will be equivalent to 3 joules per coulomb, or 3 volts. Alright, so that's why when we have cells arranged in a series arrangement, the cells are able to provide higher voltage. That means each coulomb of charge is given more energy. Now, we put them in series arrangement when we have loads that require a little bit more energy for it to work well. So if you do not supply the enough voltage to, let's say, a light bulb that is supposed to work with 3 volts, instead you supply it with only 1 volt, then of course the bulb is just not going to be as bright as it's supposed to be lah. Now, batteries or cells can also be arranged in parallel arrangement. Alright, and the function is this. It's just that these cells will last a longer time overall without the need for you to change this cell again. Alright, so you use this in applications where, you know, it's like you put and then you forget, like maybe the clock in your house. You put it and then you put it in 2 batteries, and it's designed to be able to take in 2 batteries in parallel arrangement, such that what happens is this: when I have 1 coulomb of charge, this coulomb of charge cannot take both pathways of the battery at the same time. It can only take one path, because remember, a charge is literally just a physical object like an electron, right? So as it moves here, then it can only literally take one path and then be given 1.5 volts, which is just 1.5 joules for every coulomb of charge that pass by. So because each charge will only take one path, maybe the next charge will decide to take the lower path, alright, the drain on the batteries overall will be less, so the cells will actually last a longer time. So it's like a plug and forget until it will last a long time lah. That's the intention of it. Now, what is potential difference then? Potential difference, also known as voltage, across a component is actually the work done. Remember, work done is just energy measured in joules to drive a unit charge. A unit charge means 1 coulomb of charge through the component. Now we symbolize this potential difference with V, and the formula looks very much the same as what we had for EMF, which is just work done per unit charge. The V formula, the voltage formula, is also the same. So joules per coulomb, and therefore the units for potential difference is also the same as EMF. Now, then the question becomes, what on earth then is the difference between EMF and PD, and why do we make the distinction? Alright, so EMF, you can think of it as the amount of energy supplied by the battery to each coulomb of charge for it to complete its whole journey throughout the circuit. So you can think of it as how much input energy you give to the coulomb of charge. If it's 3 volts, that means each coulomb of charge is given 3 joules of energy. Now, potential difference, however, is, in a sense, you can think of it as measuring where the energy that you supply, where does it go to. So imagine I have a bulb that is connected in series here in a circuit, and I tell you that I measure the potential difference and it's measured as 1.5 volts, which means, remember, as my coulomb of charge passes by here, there's nothing that is draining away its energy, so it still has 3 joules because the wires are supposed to have no resistance. And now I tell you that the potential difference measured, or how much energy I lose here, is actually 1.5 volts or 1.5 joules per coulomb, which means this 1 coulomb of charge gave away 1.5 out of its 3 joules. It will end up here with 1.5 joules. Remember that at the end of the day, my 1 coulomb of charge, just before it entered the battery, or once it exits the last portion of the component, it should end up with 0 joules, which means then I can then predict what is the voltage here, because for each that coulomb of charge, it must spend 1.5 joules per coulomb, or 1.5 volts. Alright, so the power of the potential difference is actually, what I would want to do is to actually place my voltmeter from here to here, and that will allow me to then measure how much energy I lost over here. While the EMF, you can think of it as how much energy is supplied or how much energy I have to spend throughout the whole circuit. But potential difference is literally, if I want to measure the potential difference across the bulb, I put one of the components, one LED of the voltmeter before, one LED of the voltmeter after. If I want to find the combined potential difference loss across both bulbs, then I put one here, and I put the other end of the voltmeter on the other side here, and then that will end up giving me 3 volts. Now, how the voltmeter does this is it measures how much energy you have at the start prior to wherever you start, just at where it's connected here, and then it measures the amount of energy you have at where it's connected at the end. If you have 3 joules here and you have 0 joules here, then it knows you have spent 3 joules of energy getting across these two components for each coulomb of charge, which is then equivalent to what we know as 3 volts. So that's how potential difference is understood. Right? So this, the voltmeter should be connected in parallel, and I think I explained quite a little bit of this when I drew this here. It is because I connect the voltmeter at the positions where I want to measure the energy before and the energy after that component. So if I put it here, let's say 3 volts, and there is no energy loss here, this will be 3 volts. At the end, just before it enters, it's supposed, or once it exits, the last component is supposed to be 0 volts. What the voltmeter does is it just measures this one, and it measures this one, and it takes this minus this, and it tells me, oh, you have spent 3 volts over on the bulb. So that is how the voltmeter works. Now, the voltmeter is in parallel because you must remember that I do not want the voltmeter to be a part of the circuit that I'm measuring. It is meant to be an observer. I'm just observing, so I do not want any current to flow here. While the ammeter is connected in series, because the ammeter's function is actually to measure how much current passes by it. So it needs to be in the direct path of the current for it to be able to tell you or tell me how much charges are passing by it per second. So that's why it's able to give me the current. While the function of the voltmeter is to just identify how much energy I have here, how much energy I have here, or rather, in this sense, I will call it how much potential I have here and how much potential I have here. I take this minus this, and it tells me the potential difference. That's why it's known as potential difference. I measure potential here, I measure potential here. It gives me the difference in the potential. Now, a quick summary of what EMF versus PD is. EMF is associated with the electrical energy source because it is considered, you can think of it as how much input energy is given for it to travel across the whole circuit, while potential difference is a little bit, you can play around with it a bit more because it's not only through one component. If you have multiple components in the circuit, I can literally put anywhere and ask you identify 2 points, and then I ask you to find what's the potential difference between those 2 points. So for example, over here, if I put my voltmeter here and here, what I'm finding is the potential difference across B. If I'm asking you to find the potential difference across A and B combined, then of course I just put one before A and one before B. One after B. If I'm tasked to find the potential difference between B and C, then I put one before B and I put one after C, and that will just tell me what's the potential difference. Now, if I connect it like this, then it will also tell me the potential difference across A, B, C. But now you know that A, B, C just makes up the entirety of your component of your whole circuit. So this value should be the same as EMF. VA plus VB plus VC will end up giving you EMF because that is my entire journey. And EMF, you must remember, is how much energy I have to go through the whole circuit. Alright. Voltage, however, any 2 points or any components I want to identify, I just put one before and I put one after. Alright. EMF is present even when no current is drawn, while PD is 0 if I do not have current through it. So just a quick question here. If I put a voltmeter here, what is this voltmeter reading showing? This voltmeter reading, what it's showing is actually the potential difference across the bulb, because you see it's one before, one after. Now, it is a little bit of a trick question because this also tells me the EMF of the electrical source. Because at the end of the day, my whole circuit is just made up of one bulb, which means if I have a 3 volt bulb, a 3 volt battery, that means all the energy supplies will go to the bulb, which means it's 3 volts here. So in a sense, just by measuring here, it will also tell me what is the EMF. Now you can also think of it as if I move the arm of my circuit and I move it over here, and I move my arm over here, it will still give me 3 volts because anywhere along this portion and anywhere along this portion, I have not lost any energy. So here I should have 3 volts and here I should have 0 volts. All right, you must then remember is how do I measure EMF? If you want to measure EMF, you put one before and after the battery. So because everywhere along this path, my charges will have 3 volts, and anywhere along this path, my charges will have 0 volts. This and this is essentially the same. That's why A and C. Okay, let's talk about the second last portion of this chapter, which is resistance. Now, I mentioned resistance already a few times in this whole chapter, but what exactly is resistance? Now, a resistance, you can think of it in the water analogy as an obstacle along the path. But I think it is much easier for you to imagine and put yourself into the role as an electron. Now, imagine an electron going through a certain load, going through a certain, let's say, wire, and the wire does not have 0 resistance. It is a wire, we call it a resistance wire, so it does have resistance. Now, you need to remember that while the electron can travel through a wire, but the wire is essentially still an object, and an object is always made up of atoms. All right, so what does kinetic model of matter state? The kinetic model of matter states that any object is made up of tiny particles called atoms, all right, and that these atoms are continually vibrating, and a solid is vibrating about a fixed position. All right, so what essentially is happening, or to the electron, what is happening to an electron, or what rather the electron experiences as it's trying to move through, is that you will see this bunch of things that are blocking your way, and you as an electron, which is a subatomic particle smaller than an atom, you have to actually squeeze through all these little gaps to get through the wire. Now, you must remember that one electron only has 1.6 times 10 power negative 19 coulombs. So for 1 coulomb of charge to pass through, can you imagine that I have so much electrons trying to squeeze through here? So because of that, and because of the tightness of the space, and you must remember also that the atoms are made up of a nucleus that is positive because it has protons inside, so they do attract the electrons a little bit. So at the end of the day, what you have is the electrons trying to squeeze its way through all these little gaps, and I have 10 to the power of 19 billions and billions of electrons all trying to squeeze through at the same time. So that is what resistance is. Alright, so resistance is a measure of how difficult it is for an electric current to pass through a material. Alright, it is a property that restricts the free electrons in the material. Now, the resistance of a component by definition is the ratio of the potential difference across the component to the current running through the component, which means R equals to V over I. Now, I need you to recall then the units of V, voltage, and the units of I as voltage, volt, and ampere, which also can be known as joule per coulomb and coulomb per second. Now, that's a lot of units here. It's all very complicated. So you can have a combination of all of these units combined together, and then you get a complicated looking set of units, or you can just summarize it and call it the ohm. Now, the resistance, or the unit of the resistance, is ohm. It's written with a Greek symbol omega here. Now, one important thing for you to note, especially important for the later chapters, is that when I'm calculating R equals to V over I, and let's say I'm calculating the resistance of the bulb, I must use the voltage of the bulb, and I must use the current that is running through the bulb. Now, it might seem very obvious to you, why would I use a voltage that is not of the bulb to calculate the resistance of the bulb? Now, in later chapters, especially on DC circuits, things get pretty complicated when we have circuits that have a combination of parallel and series, and you have so many different voltages and so many different currents. So this is an important tip for you when you are using R equals to VI. Make sure that you are using the correct voltage and using the correct current. Alright, now how do I measure resistance? At this point in time in your study, based on your definition or the formula for resistance, I need to know the V and I need to know the I before I can calculate my R, which means I need to know the voltage and I need to know the current running through the bulb before I'm able to find my R. Now, so what is important to note is that while this is how you should know, how you learn how to calculate resistance, there are some electrical equipment that allows you to measure resistance directly, like the multimeter, right? But essentially right now, if I want to find resistance of this bulb, I need to measure the potential difference across the bulb and the current that is running through the bulb. Alright, now this slide is pretty important, so I need just to tell you this. In any circuit diagram question or circuit question, you do need to make the assumption that the resistance and the wire and the ammeter or any connecting points, objects like the switch, are supposed to have zero resistance, while the voltmeter is supposed to have infinite resistance. Why so? Because remember, my ammeter and voltmeter is supposed to be just an observer of the circuit. I'm just here to measure the current. I'm not here to take part in the circuit. Same here with voltmeter. I'm just here to observe the PD of the bulb, not here to take part of the circuit. Alright, if my voltmeter does not have infinite resistance, then that means there is a chance that I have some current running through, which I do not want to have any current running through, because if I have current running through the voltmeter, that means the voltmeter becomes part of the circuit. That's why my resistance of the voltmeter must be infinite. The same goes with the ammeter. My ammeter is there just as part of the observer. I do not want to participate in the circuit. If I have non-zero resistance, means my ammeter is not zero resistance, then some of the current will actually, or some of the charges will lose some of its energy here, which means that this has taken part in the circuit, which is not what we want. Alright, so resistors are components that provide resistance. There are two types that you need to know: fixed and variable resistors. This is how fixed resistor, this is what fixed resistors look like, and this is what you know of as variable resistors. Now, variable resistors consist of a slider that can move left and right along here. I've just shaded it, surrounded it with the, penned it with the red line here. So you know this is the slider, and there are a few connection points that are metallic, so which I potentially can connect my connecting wires here, 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 and here. Now, how you work a variable resistor is that I must connect it diagonally, one here and one over here. Now, the variable resistor is made up of a coil of wire, resistance wire, that is coiled very, very tightly. And here I have a metal bar. So what happens is, if I want to have very, very low resistance, remember, variable resistors or rheostats are resistors where I can vary how much resistance it is. So if I want to have very, very low resistance, then what I will do is I'll put the slider all the way to over here, which means any current that is passing through, what will happen is that the current will go through here, up through the slider, where the slider is now here, cut through here, and then just exit out bypassing the resistance wire. If I would like it to have maximum resistance, then I put the slider all the way up to over here. Then what that will force the current to do is that the current will have no choice but to go through all the resistance wire here, all the way to the tightly coiled wires before it can exit out here. So in a sense, that is maximum resistance. If I want to have any resistances in between, then I can put it at anywhere, whether here or here, then I will have a varying resistance. Alright, so let's do a quick question here. You can pause and read the question. I got a 3 volt source connected to a light bulb. The ammeter registers a reading of 0.2 ampere. So 3 and 2 ampere, and they are both related to the bulb. Now, how do I know that the 3 volts is at the bulb? Because the 3 volt is actually the source. But if you look at it, my whole circuit is just made out of the bulb, which means immediately I know this must be 3 volts. Alright, so now I know the volt PD across the bulb, and I know the current across the bulb. I can just then use V is equals to, oh sorry, there's nothing for me to do here. V is just equals to the EMF, because it is the whole component, which means it's just 3 volts. If I'm required to find then the resistance of the bulb, I just use the formula R equals to V over I, where the voltage of the bulb is 3 volts divided by 0.2 amperes of the current. Then I will get, I believe, 15 ohms here. Alright. Now, the circuit is switched on for 5 minutes. Determine the amount of charge that is passing by. Remember, earlier on at the start, we studied when we introduced current, we talked about this formula. It is Q equals to IT, or rather I is equals to the amount of charge passing by per unit time. If I'm supposed to find the charge that passes by in 5 minutes, then I have the current here, which is 0.2 amperes. Remember, 0.2 amperes is 0.2 coulombs passing by per second. So I take 0.2 amperes or 0.2 coulombs per second, multiply by 5 minutes. But remember that it's coulomb per second, so 5 minutes doesn't cut it. I need to change it to seconds. And that will give me an answer of 60 coulombs of charge. Alright, finally they ask you how much energy is then dissipated by the bulb in that 5 minutes, where I got 60 coulombs of charge passing it by. Then I need to use the formula for potential difference, which is V is equals to work done per unit charge. Alright, so if I want to find the energy, then it's just energy is equals to QV. The amount of charge passing by is 60 coulombs of charge, and I know that 3 volts here, that means 3 joules for every coulomb of charge that passes by. I got 60 coulombs of charge that is passing by. I multiply by 3, that gives me 180 joules. So this is how I do. Now, I think this will be an important part for you. You need to be able to fill this up. I would like it if you could to just pause and fill this up by yourself. Alright, so once you're done, you can just do a quick check. Charge is Q. The unit of this is the coulomb. The formula, there's no formula for charge. The unit of current is I. The unit of electromotive force, the symbol is this, epsilon. The symbol of voltage is just V, and this is just R, resistance. The units of current is the ampere, or it can also be known as coulomb per second. Alright, the EMF is just volt, but remember that volt is also can be known as joule per coulomb. This is also the same, volt, joule per coulomb. Resistance is the ohm. The formula that governs current is I equals to Q over T. EMF is E equals to work done or energy per unit charge. This is V, work done per unit charge. And the formula for resistance is R equals to V over I. What is easier then for you is that actually the definition of all of this is just based on the formula. Rate of flow of charge, or charge per unit time, which is given by the formula, charge per unit time. Energy per unit charge, or work done per unit charge. Remember, the difference between EMF and voltage is that the EMF is your input, so it's therefore essentially the energy required for the whole circuit, while V is dependent on where you place your voltmeter and what you define as the potential difference you want to measure. It can be between any 2 points that you define, or any component. And the definition of resistance is just V over I. Alright, so I'll carry on this in a bit. Ohm's law. Alright, let's now talk about Ohm's law. So Ohm's law is a law that states that if my physical conditions, such as the temperature and whatnot, remains constant, the current that is passing through the conductor or the material will be proportional to the potential difference that is across it. That means if my voltage increased by a certain amount, provided that my physical condition remains the same, my current will scale at the same rate, which means bigger V, but the V increases by the same rate, but I will also increase at the same rate, which means bigger number divided by bigger number, the R remains the same. So essentially what Ohm's law states is that if my physical conditions remain the same, my R remains the same. Now, there are some materials that are called ohmic conductors that follow Ohm's law, means that my resistance doesn't change. Now, what is useful about knowing this is that for a normal kind of typical circuit question, you are supposed to assume Ohm's law for the resistors that are connected in the circuit, because there are some questions in the O-level that will call on you to change the potential difference or the voltage that is across the bulb. If the Ohm's law is not obeyed, then that means it's impossible for you to solve, because every time your voltage increase, and if my current doesn't scale at the same rate, then that means the bulb resistance will change, which means your question becomes impossible to solve. Alright, so there is a classification of material that obeys Ohm's law, and these materials are called ohmic conductors. Now, we use IV graph for us to imagine or show how the graph, how the ohmic conductors will react when I apply different voltages across it, and based on different voltages, how much the current is. Now, what is known, or rather, I will just tell you first, for ohmic conductors, the I versus V graph is a straight line that passes through the origin and it has a constant gradient. Now, let me explain why so. Remember that this V equals to IR is from your definition of resistance. R is equals to V over I. Now, in a typical kind of situation, the horizontal axis is always your x-axis and the vertical axis is known as your y-axis. Now, what we are trying to do is getting from here to something of the form y equals to mx plus c. Now, if you look at the equation, or rather the graph, if I am plotting a graph of I versus V, which means I is actually on my y-axis and V is on my x-axis, then what if I want to make it of the form y equals to mx? Remember, y is my current and x is actually my voltage. If I were to rearrange it, then the R will be somewhat in the gradient. So if I were to rearrange V equals to IR, sorry, let me rearrange this here. V equals to IR. I would want the I to be on the left side here, right? So I just rearrange IR equals to V. Then, but I want the I to be by itself. So I bring the R over. I have V over R. But then again, I want my V to be by itself here. So then my equation just becomes I equals to 1 over R multiplied by V, which is what I get here. So now I have now manipulated this equation to fit the form of this, where I is my Y, V is my X value, and M is my 1 over R. So now I need you to remember that M is actually just gradient. So if your gradient is 1 over R, so let me work backwards because it's easier. Ohm's law states that the resistance will remain constant. If my resistance is constant, therefore my 1 over R is also constant. If my 1 over R is constant and I have a gradient, 1 over R is equivalent to my gradient, which means I have a constant gradient. So this is the first thing explained. Alright, I also note that I do not have a plus C. Plus C means is your y-intercept, that means it cuts the y-axis at 0, which means this is it. So for an IV graph of a ohmic conductor, this is what it will look like. Now, sometimes O-level will try to mess with you. Instead of giving you an IV graph, they give you a VI graph. And the VI graph is actually much easier to deal with than the IV graph. So now the question begs is, if VI graph is much easier to deal with, why am I even given IV graph in the first place? Alright, so you must recall in your study, or rather by convention in any of the sciences, what goes on your horizontal axis or your x-axis is usually the independent variable. And in any circuit, the one that controls how much current, which is the dependent value, is actually your V. So traditionally, your V will always be on the horizontal axis. That's why it's always presented as IV. Now, let me explain why the VI graph is much easier. So the VI graph means if I were to change this into the form y equals to mx, remember VI graph means is V goes on my y-axis and I then goes on my x-axis. That means this form is already of the y equals to mx plus c form. Because my V is on the y, it should be by itself here. My I, which is the x-axis, should be by itself here. That means when I manipulate this, my R naturally becomes my M, which is the gradient. And the gradient becomes R. And remember that in ohmic conductors, your R is constant. Which means in a VI graph, my gradient, which is equivalent to R, will be constant. Now, there are some classification of materials that do not follow Ohm's law, and these are called non-ohmic conductors. Alright, so basically if Ohm's law means R is constant, non-ohmic conductors which do not follow Ohm's law basically means the R is not a constant value. Alright, so let me just state first, the IV graph for non-ohmic conductors is they are not straight lines and the gradient is not constant. So let me run through. There are two objects that you need to know, or rather understand. No, you need to memorize the shape of the graph. All right, so the first one is the filament lamp. So let me just explain the end first. Why is it that filament lamp, the resistance will increase as I apply more voltage? All right, so the understanding of this is this. If my voltage increase by V equals to IR, when my voltage increase, my current will also increase running through it. All right, which makes sense because voltage is just joule per coulomb. If I have more energy given to each coulomb of charge, that means my current can actually go through faster. All right, so as current increases, there's more energy or thermal energy that is generated. Can you imagine this? If my electrons, I suddenly have a lot of electrons trying to rush through the wire, all right, some of the electrons is going to lose and drop its energy on the wire, which means the wire is going to start to heat up. Now, when the wire heats up, the temperature of the wire increase. Then you must recall that when I study my kinetic model of matter, the higher the temperature, the higher the kinetic energy of the molecules. So now my electrons, who is already struggling to go through, what is happening is that when the temperature of the wire increases, these atoms here that make up the structure of the resistance wire, is these fellas are actually going to vibrate even more vigorously, which means it's going to make even harder for the electron to go through. So therefore, I overall have an increase in resistance. So the filament lamp, when I have high voltages, high current, it will result in a resistance increase. So now let's talk about your IV graph again. I do the same kind of argument. I start with V equals to IR. I make it of the form Y equals to MX. Remember, this is my Y-axis. Sorry, this is my X-axis and this is my Y-axis. I try to make it I here, 1 over RV, which means my gradient is equivalent to my 1 over R here. All right. So just now we said the higher my voltage, the higher my resistance in the filament lamp. So the higher my voltage, the higher the resistance. That means I'm aiming for a resistance increase. When my resistance increase, I divide my resistance here increase, which means my whole 1 over R, because now my R is higher, my 1 over R is going to be lower, decreasing, which means my gradient is decreasing, which means then I have a decreasing gradient graph. Now, if I have a VI graph, all right, please do this yourself. All right. Once you are done, you can just listen to what I have to say. V is equals to Ri, Y equals to Mx. So if I'm putting it Vi, this is my Y-axis, this is my X-axis, my R is directly my gradient. So I'm for a filament lamp based on this, the higher my voltage, the higher my resistance. So my gradient, which is my R, is increasing. All right. So if my R is increasing, my gradient is increasing. So if I have a VI graph, I will end up with an increasing gradient graph. All right. So the last of the non-ohmic conductors, or the second of the non-ohmic conductors, which is actually the last of the non-ohmic conductors that you need to remember, is a semiconductor diode. A semiconductor diode is a device that only allows current to flow in one direction, which means when current is flowing in the correct direction, or rather when voltage is applied in the correct direction, current will flow normally. Current will flow like it is a normal resistor. All right. However, when you try to apply voltage in the opposite direction, which means I swap the battery, then the current actually hardly flows. So if you see over here, if I put it in the reverse direction, the resistance is so high that I have barely any current flowing through. All right, so this is the IV graph of a semiconductor diode, which brings us to the last portion of the chapter, resistivity. All right, and the final portion of this chapter is called is for resistivity. Now, what is resistivity? So imagine we are talking about an electron. So imagine again you are the electron, and the electron is traveling through a length of a resistance wire. Now, you remember that when we talked about and we discussed about how electrons travel through a wire, that the wire is made out of all these atoms, and these atoms will then provide the resistance by blocking its path or causing it to be attracted. So what we are talking about in terms of resistivity is we want to find some things that will increase the resistance. So if I have a length of wire and I double up the length of the wire, this means that the electrons not only have to go through once of this wire, it has to go through a second time, which of course then increases the resistance that is felt by the electron, because instead of just having to go through it once, you have to go through it twice lah. So in a sense, the resistance of a wire or any resistance wire is proportional to its length. The longer it is, the more resistive, rather the higher the resistance felt by the electrons. Now, and again, if the electron is going through a wire, the larger the cross-sectional area of the wire, the less resistance it will feel. So you must remember again that one electron only has a charge of 1.6 times 10 power negative 19. So essentially, for 1 coulomb of charge to pass by, I have a lot of electrons all at the same time trying to squeeze through the wire. Alright, which is made easier if I have a higher cross-sectional area, because then there's actually more space for the electrons to squeeze through. Now, which means that the larger the area, the lower the resistance of the wire. So when we say this is inversely proportional. Now, so when I combine these two, then what I have is a relationship that says resistance is proportional to the length of the resistance wire and inversely proportional to the area. Now, of course, if I have the exact same wire, sorry, not the exact same wire, I have the same dimensions of two different materials, you cannot say that these two will definitely have the same resistance, which means I have the same length, same cross-sectional area, but one is, let's say, copper and the other one is made of a material like, say, rubber, an insulator. So of course you're going to say even though the length and the area are the same, the conductivity or the resistance that is felt by the electrons trying to go through will be definitely higher for this one, which is the rubber one, compared to the one with copper. So which means we give this term based on the material, the term called resistivity. Alright, so altogether the resistance of wire depends on a few things. One, length, one, area, and the third one, resistivity, which is basically the material that is made up of. Now, rewriting that, I have the formula R equals to rho L over A, where rho is the resistivity of the material, yes, and rho is the same formula, or sorry, same symbol as density. Alright, so if I were to rework this, I have resistivity is resistance times area over length. Recall that the formula for, or rather the unit for resistance is ohm, area is meter square, this is meter, I combine it all together, I got ohm meter square over meter, which means that the unit of resistance is the ohm meter over here. Alright, so resistivity is a property of the material and it is independent of the dimensions. So as example, if I have an insulator versus a conductor, then of course the conductor will have a lower resistivity compared to the insulator. The higher the ability of a certain material to block the electrons from going through or making it harder for the electrons to go through it, then I say the resistivity of the material is higher. Alright, so these are some examples and samples of various resistivity. You don't have to remember any of them. The way we ask the questions in relation to resistivity is based on comparison with a certain wire. So let me give you an example of a question. So take some time to read the question. So I got a length or resistance wire 50 cm connected to a 3 volt battery and the ammeter reading is given as 0.15. They ask you to find the resistance. It's just again R equals to V over I. 3 volts divided by 0.15, I get the value of it being 20 ohms. Now, they say I then double the length of the resistance and the cross-sectional area is half. Can you determine the new resistance of this new resistance wire? So how would you go about solving this question? Logically, you can think about it like this. If I double up the length of the resistance wire, this means my electrons have to go through not only just one time, it has to go through the trouble of going through the same resistor again the second time, which means I'm expecting the resistance of this new wire to double just based on the dimension of length. At the same time, the cross-sectional area is half, which means initially it was this big, the wire, now the cross-sectional area is half, which means I have less space. As compared to the earlier one, I'm expecting the resistance from this fella to actually also double up because I now have less area. It's harder for my electrons to move through because the area is smaller. So logically, because the resistance double up because of the area and double up again because of the length, then all I need to know is then double times 20. The new resistance wire is just 20 times 4, and that will give me an 80 ohm. Now you can solve and write the answer like this, and that will be perfectly fine. But the way that I usually like to do things so that it's easier for you to see is R old wire, this is the old wire, is equals to resistivity times length of the old wire over the area of the old wire, and that gives me a value of 20, which I calculated over here. Now the new wire is then of course correspondingly the same resistivity because it is the same material, but the length I'm talking about is the new length over the new area. So then I try to put the length of the new in comparison to the old. The new length is actually double the old length, so that's why I put at 2 times length of the old one, while the area is half of the old area, so it's times 0.5. So from here to here, all I do is I just draw out, or rather I draw the length old and area old, and which means I have this number here, and then this number, if you compare to the first statement, is just equivalent to 20, right? Because this is 20 and this is the same as this one. So 20 times this one, and I'll get the same answer, 80 ohms. So this is the kind of questions that you will get asked for whenever you are tasked to find, or rather, a resistivity question. Now, some other things that they might ask you to find is to actually use calculate resistivity. Of course, then they may give you the diameter. So again, resistivity equals to RA over L. So all I need you to be careful is that you should change the length to meter and the area should change to meter square before you do anything. Alright, so, and also of course you should know that the area of a circle is pi r square in that sense, and then after that you just solve. Alright, so I just leave the solutions here for you to have a look at it. One other important thing, or rather one other thing that O-level might ask is, instead of giving you cross-sectional area is triple, they may give you things like the let me give you an easier example. The radius is now 3 times the original radius of the wire. So how does tripling the radius actually affect the cross-sectional area? So you do need to know how to do this. So if the area is given by pi r square of a wire, the new area is still pi r square, but my r, sorry, I'm drawing diameter here, so I should be drawing r. So the new r is actually 3 times of the original length. So it's 3r then square, which means pi 9r square, which means it's 9 pi r square. So if I compare this area, which is the new area, compared to the old area, it is actually 9 times more, right? So an easy way for you to think about it, whatever I increase it by, because the function carries the square on the radius, or the dimension of the radius, I square the number it is increased by. So if it's 3 times the radius, then I just 3 square the original and then multiply by the area, I get 9a. So if my radius is increased by 4 times, then I 4 square, and my new wire will be 16 times the original area. Alright, so the very last portion that I'm just going to cover is how would you describe a procedure in which you would find the resistance of a resistor, and how can the resistance be calculated if I were to be examining the resistor over different potential differences. Now, the first instinct for most students when they ask you to calculate the resistance of a certain wire is just to take R equals to V over I over just 1 . So basically I have a circuit over here, I calculate the V here, I calculate the current going through, then that will give me a good description of what is the resistance. But the actual way you should do is that you actually should test this resistor over a various range of voltages, and then you basically plot a VI graph for you to go and find. So how do I then test the resistor over different voltages? You can simply do it by adding a variable resistor in this component of the circuit. So by changing this resistor here, I can then control the voltage that is felt over here, and therefore I can test the voltages coming through here over various no, I can test the current that will flow through this resistor over various potential difference. So I'll leave this to you to go and have a read, but basically it means that I should just set up the circuit as shown here, record the ammeter and the voltmeter reading. I change the variable resistor that will then change the voltmeter reading that I feel or that is felt over the fixed resistor and the current. I repeat until I have at least 5 sets of IV, then I plot a VI graph. Alright, so when I plot a VI graph, remember the formula is V is equals to RI. When I plot a VI graph, this is on my y-axis, this is on your x-axis. Alright, which means this is y, this is x, and R is my M, which means my gradient of this VI graph here will tell me what is the resistance. And then based on this, I use the gradient value or how to calculate gradient to get the value of the resistance. In general, for a VI graph, the larger or steeper the gradient is, the higher the resistance. The lower the gradient is, the less steep it is, the smaller the resistance. Alright, so now just to summarize what we covered, I know this chapter is not an easy one, but it does form the foundation for your future electricity chapters. So I'll just do a quick summary. Charge, the unit of charge is the coulomb, and it's written with abbreviated by a C. The unit, the symbol of charge is Q. For current, it is I. Electromotive force, the symbol is E epsilon, or you can write it sometimes just as EMF. The symbol for potential difference is V, sometimes can be written as PD. The resistance is universally known as R. The unit of current is the ampere, written with an A as such, or sometimes we can also say it's coulomb per second, right? Electromotive force is the volt, abbreviated by V. It's also known sometimes as how much joules or how much energy is each charge has. PD also pretty much the same, volt V, joule per coulomb. And resistance, the unit is the ohm, but is written as the omega symbol. Alright, so talking about definitions of what these things are. Current is just the number of charges per unit time, the number of charges passing by per unit time. EMF is the work done per unit charge for that charge to travel through whole circuit, through the whole entire circuit. Alright, while PD is just the work done or how much energy each charge is given for it to travel, or how much energy it loses for it between any 2 points that you identify on the circuit. And the resistance is just the ratio of PD to current. So while these are the definitions, the formulas are also take reference from the definition. So that means current is charge per unit time, EMF is work done or energy per unit charge, V is also work done per unit charge, and resistance is equals to V over I. Now, how do you measure current? You measure current using a device called an ammeter, and it's placed in series. Electromotive force is a voltmeter, and you place it in parallel either across the electrical source, because EMF has to do with the source, or between before the first component and just after the last component of the circuit, because that essentially is the electromotive force. Because remember, your electromotive force is the energy required for it to travel through the whole circuit. Potential difference is the voltmeter, also in parallel as well, but this one is literally between any 2 points in which you want to measure the potential difference of. And resistance, if you want to measure resistance, although there is a way for you to measure it directly, but at your level you are supposed to know that I must have the voltage and I must have the current for me to be able to do so. So therefore, the voltage, you need a voltmeter to put in parallel across the bulb, and for the current, you need an ammeter to place in series with the resistance. Right? And the last portion of the chapter that we covered about R equals to rho L over A, or has to do with resistivity. right? So, and this is useful for us when we want to have change the dimension of certain resistance wire. Then it allows me to predict the new resistance of this new wire. So for example, I give you a piece of wire that is 10 ohm. Now I say that I've changed the dimensions of the wire. The material remains the same, but now the length is double and the radius of this piece of wire is now double. So you remember that when your radius is double, because your formula for area is pi r square, the radius is double. That means my I need to square the increase. So if it's double, I square the increase, the area will actually be 4 times the original area of this one. So how do you solve this kind of question? What do you write? You just write the radius of the resistance of the new one is r rho l over a, new wire over area of the new wire. Then all I do is, if the length is double, I just put 2 here. This L and A references the old wire, and the radius is double, which means the area of the radius is double, which means the area of the wire is now 4 times. So I put over 4, and I replace this rho L over A, which gives me the resistance. This whole chunk is the resistance of the old wire, which means it's just 10 times 2 over 4, and the answer is then just 5 ohms. This is the length of the resistance of the new wire. Ohm's law is a law that states that the resistance will always remain constant, provided all my physical conditions remain the same, like temperature. I start off with the VI graph because it's much easier for us to imagine and manage. So if I were to rework this formula into the form such that it's y equals to mx plus c, this is what I will get, because V is on the y-axis here, because it is a VI graph, I try to rework such that the V is on the left side, the X is my current I here, and therefore that will give me the fact that the gradient here is equivalent to R. And Ohm's law tells me that the resistance is constant. If resistance is constant, that means the gradient is constant. So for an ohmic conductor, the VI graph, this is what it will look like, a gradient constant graph. For the IV graph, I still use this same formula, but I rework it such that the I is on one side and the V is on the other side, correspondingly because of the Y and the X axis, which means that my gradient is actually 1 over R. Remember that Ohm's law states that the resistance is constant, which means if my gradient for IV graph is 1 over R and this fella is constant, this means the gradient of the line is also constant, which means essentially it's still a straight line graph whenever I have an IV graph for an ohmic conductor. For non-ohmic conductors basically mean the resistance does not remain constant, it changes. And you need to know specifically two examples of non-ohmic conductors. One of them is the filament lamp. For the filament lamp, we did explain why the resistance will change, because as I increase the voltage or the potential difference that is felt across the lamp, the current consequently will increase. And because the current increase, I'm expecting the temperature of the wire to increase, and the temperature of the wire increased by kinetic model of matter. I know now that the atoms that make up the wire will be vibrating even more, which makes it more difficult for the electrons to want to go through the wire because the atoms are now vibrating more vigorously, which means the resistance will increase. So how does the VI graph, what is the VI graph of a filament lamp? How does it look like? I just use the same formula, V equals to Ri, where R is my gradient. My gradient is equals to R, and my R is an increasing value, which means my gradient is an increasing value, which means for a VI graph, I'm expecting an increasing gradient graph for the filament lamp. For IV graph, it's the same kind of argument, Y, M, X, which means my gradient is my 1 over R. For filament lamps, my resistance is increasing, which means this whole number is decreasing, which means my gradient is decreasing. So an IV graph for a filament lamp is a gradient decreasing line, and the gradient decreasing line basically is steeper become less steep. So this is what the IV graph will look like. And finally, for the diode, for diodes, how it will look is basically in the forward direction where a diode is supposed to work, then my IV graph will just work normally. But in the opposite direction, we call it the reverse direction, then even if I increase the voltage a lot, I hardly have any current coming through, almost none. So this is how the IV graph will look like for a diode. You should also go and explore how the VI graph will look like. Alright, so this is the end of the chapter. So please review all of the summary and the notes. I know it's not an easy chapter, but absolutely remembering this and understanding this will help you in your study of your future chapters down the road for electricity. Thank you.